So, in this lecture we will continue with the discussions what we had in the last class. This lecture will be lecture 7 on module 2, where we are focusing on dynamics of ocean structures, an example application to articulated towers. We have picked up an example in the last lecture, we wrote down the equation of motion. So, let us rewrite the same equation once again and see what would be the scheme of solution what we want to handle for the specific problem, which we call as an iterative frequency domain. This was the equation what we had as the equation of motion in the last lecture. I will rearrange this back again, which we already did. So, further I can rewrite this equation slightly in a different manner, saying so I call this as f of t, which I write as equation number 13. So, in this equation number 13, the displacement values, the displacement amplitudes basically in my case displacements are rotation at the base of the tower are unknowns at any frequency. They are unknowns at any specific frequency. Further, f of t, beta of t, k nu of t are functions of rotational displacements. Hence, the solution becomes iterative. Why iterative? Because the right hand side of this equation of motion f of t is a function of the left hand side of this equation of motion, which is displacement. So, you do not know actually, because as long as you do not know the displacement, you will not be able to solve this equation of motion. Okay. So, we have to assume certain value and keep on iterating. In addition, all these functions are also been shown in the last class, they are functions of displacements which are non-linear as well. Therefore, we follow iterative frequency domain. That is the reason why we follow this procedure. The moment I say is chosen, then equation 13 is to be solved in frequency domain. Equation 13 is the rearranged equation of motion actually. The moment we agree that I must solve equation 13 in frequency domain, then I must decompose thetas and f in Fourier components, because I want to look for the frequency content of the loading. Therefore, theta of t and f of t are now decomposed into Fourier components. The moment I say Fourier components, then they will have cosine and sine values and a fixed amplitude. So, let me write those values here. I will remove this. So, theta of t and f of t can be written as theta 0 f 0 summation m equals 1 to p of the sine component and the cosine component So, I say theta mc cos m sigma t. So, here I write fmc cos m sigma t. So, this is a negative component actually. In Fourier component you will see this is going to be negative, because the coefficient will become negative. Theta ms and fms sine m sigma t, sine m sigma t. I call this is equation 14 and 15. So, now where theta 0 and f 0 are real valued vectors at 0th frequency. Whereas theta mc and fmc are values at mth harmonic, that twice this m is there, of the cosine component. Whereas theta ms and fms are values of sine component. Now, the summation p is the number of harmonics you are considering in your analysis. Summation p considered for the wave load. and of course sigma, write down here, is 2 pi by RL, where RL is called record length, or sometimes is also called as T, which is period of the wave loading. I can also find F0, Fmc and Fms in further integrable form, because they are in summation series. I can easily find out that as F0 Fmc and Fms can be given as 1 by record length of 0 to T of f of t, capital F of t, sorry. This 2 by record length of 0 to T of f of t cos m sigma t dt, whereas Fms will be minus 2 by record length of 0 to T of f of t sin m sigma t dt. Let me call these equations as 16, 17 and 18. I will remove this. Now, the equation of motion can be expressed as, in a simple form, I say psi of m is psi mc and sin ms, where 90, where psi mc and sin ms can be given as a matrix of omega square minus m sigma the whole square minus 2 zeta omega m sigma 2 zeta omega m sigma and omega square minus m sigma the whole square of theta mc theta ms, which is equal to, sorry, minus, because I need the minus value also as well, minus Fmc and Fms, which can be now set to 0, that is RHS. Equation 20. In simple terms, equation 20 can be rewritten as psi of m km theta m minus Fm is 0. I call this as 20. So, these are all vectors of size 2m by 1, whereas this is size 2m by 2m. Now, let us look at the hydrodynamic loading part. Now, for the hydrodynamic loading, we already know that f of t is a function of theta dot. You just see equation number in your literature 11 and 12. If you look at equation number 11 and 12, it is clear that f of I or f of I plus 1 is a function of the angular velocity of the tower. And therefore, hence equation 19 becomes iterative. Equation 19 is the modified version of equation of motion in frequency domain. Now, how will you solve an equation which is iterative in nature in frequency domain? One can use the classical Newton-Raphson technique. Question 19, but the Newton-Raphson technique is computationally expensive when you apply for one, high multi-degree freedom system models, 2, when the system nonlinearity is higher. So, what is the alternative solution for this? People use Jacobian. So, without modifying the convergence criteria and quality of results, one can evaluate. So, evaluate Jacobian in the scheme NR stands for Newton-Raphson scheme. So, now the question is, what is the compensation you make, or what is the compromise you make when you evaluate Jacobian of NR scheme? Because we must know the limitation of this problem, we make certain compromise on this. Let us clearly state what is the compromise we have to make when we follow a simplified solution of this nature here. The compromise is, we already know that f of t is a function of theta dot. So, it is a derivative of the displacement. So, if you want to really find f of t at I is equal to 1, you must have the derivative of the displacement at I is equal to 1. is that clear, because it depends on the theta dot at that iteration. What I will do here is I will take the theta dot of the previous iteration and use it for the next iteration. Okay, that is the compromise I am making here. The f of t should be a function of theta dot of that iteration itself, but what I am trying to do here is pick up the theta dot of the previous iteration, use it for the next iteration. That is the compromise I am making. Okay, that is how the solution can become slightly simple. So I write here the derivatives. I write derivatives in plural because there are theta dot and theta double dot, both are available in f of t. Okay, so the derivatives of mth harmonic with respect to qth iteration or qth harmonic of any node or ignore, provided m is not equal to q. This is a first level approximation. This is the compromise I make in evaluating Jacobian for the Newton-Raphson scheme. So proceeding further, let us set the equation for any, let us say, rth iteration and see what happens. Any doubt here? So I leave a question here that you study some material and advanced mathematics or applied mathematics and try to understand for a given function how to evaluate Jacobians. They are available in standard literature. If you want, I can do a small problem in the next lecture just to take up a function and evaluate Jacobian for that function. You must know how to evaluate Jacobian for a given scheme. Any questions here so far? So we move on to equation number 21, where I have set the equation of motion in the frequency domain, which will be obviously iterative. Since it is iterative and the non-linearities are higher, I am not using the exact NR scheme for this problem. I am modifying it by evaluating the Jacobians of the NR scheme, where I compromise saying that f of t depends on the derivative of that iteration itself, but I am picking up the previous value and keep on iterating. That is what I am trying to do. So there is a small, it will create certain error, but this will have a faster convergence and it will become, it is proven to be computationally less expensive compared to the original scheme of NR. Therefore, the equation for rth iteration becomes, now I want to have the governing equation for the iteration scheme, where I will now use the Jacobians, where J m of r, that is a Jacobian, theta m of r is equal to, these are all r, they are not mu, okay, rth iteration, some iteration in the scheme. So simply equal to Jmm of r theta m of r minus 1, okay, that is what I am doing here, r minus 1, the previous one, minus of course the psi values, okay, that is my frequency components of the forcing function. So 22 is the number running, right, whereas Jmm is given by dou psi m by dou theta m, that is a Jacobian, which is alternatively Km bar minus Fm bar. 23. So, partial derivative of the frequency component of the forcing function with that of the displacement, because I am actually finding out the solution on the displacement. That is why the denominator in this case is displacement, where Km can be written as, or Km bar can be given by the original equation what we wrote earlier. Let me repeat it again here, omega square minus m sigma the whole square minus 2 zeta omega m sigma 2 zeta omega m sigma omega square minus m sigma the whole square, which is Km bar. Though I am numbering it again, but already we wrote this equation. Okay, we already have this equation with us. Now, f of m is tricky, that is where the problem starts. This is given by again a 2 by m by 2m matrix, where I say see here how I am writing it, mc ms, this is also mc, okay, this rho of mc, this is rho of ms, this is rho of ms, this is mc and this is ms. So, this column is the partial derivative of the forcing function of the frequency components cosine and sine with respect to theta of the cosine component only, whereas this column is the partial derivative of the forcing function of cosine and sine component with respect to the sine component of the displacement. That is how it is written. Okay, equation number 25. Just for a sample, we will pick up one derivative and see how I can evaluate this one derivative, okay, one value. So, let us say for example, I want to evaluate mc by theta mc, that is dou f mc by dou theta mc is nothing but 2 by the record length of 0 to record length of dou of the forcing function with respect to theta mc of the cosine component, because I am talking about c here, which is cos m sigma t dt, which can be given as 2 by RL of, I am just expanding this f of t, already we have f of t with us, I wrote in equation number 13. I am rewriting it again. So, 0 to record length of derivative of f of t minus k nu t theta minus I naught beta of t theta double dot by dou theta mc multiplied by cos m sigma t dt. I write it here, okay, I write it here, cos m sigma t dt. That is my derivative here. I call this equation number 26. We rub this. So, we are now setting the equation for an rth iteration which involved certain derivatives of Jacobians. We are trying to explain those derivatives here from the original equation of motion rearranged in the frequency domain. That is what we are trying to do here. Now, here the interesting part is, if you want to look at the ith node of f of t, how will it look like? Because this is not an f of t of the whole problem, it is node by node I have got to travel, is it not? I divide the tower into the n number of nodes. I have also divided the wave loading into m number of harmonics, that is different, that iteration is separate. I am dividing the tower into n number of nodes, I plus 1, I plus 2 and so on. Let us look at ith node how this f of t looks like. Okay. So, the ith element of the load vector of this load vector, due to, of course, I am taking only hydrodynamic. Loading. I can also do this for aerodynamic loading. I am in this lecture we will discuss and focus only on the aerodynamic part of it. Is given by can you attempt to write this equation? Let us see, we already have it, we already know the classical Morrison's equation for this. Can you write what would be f of ith of t? Why I am saying f of ith of t is small letter, because it is per unit length. So, it is going to be a summation of j is equal to r minus 1 to r plus 1, 3 nodes, that is how Newton-Raphson works. I write it in a different notation actually, k ij of d, please follow this notation, I will explain this now. Vj and Vj, that is the drag component, plus k ij of m, I call this as mass component or inertia component, u double dot of j, and the summation runs for this from r minus 1 to r plus 1, where I varies from, for I equals 1 to capital N, N is the number of divisions or elements in your tower. Also, okay, I will call this equation number 27, also we know that Vj is the relative velocity between the water particle and the tower. R of course is the node element, R is the node at which you are evaluating this force, R is the node at which force is evaluated. Is my handwriting legible from the back? Is it legible? Even if it is not legible, I think you have got to adjust it, because I am writing faster. And of course, N is the number of elements of the tower, of course u dot and theta dots are water particle velocity and structural velocity respectively. Kdij is the drag, force, and Kmij is the inertia force. Of f of t. Now please note that in the equation 27 the iteration or the scheme runs for or operates for 3 nodes, that is r minus 1, r and r plus 1, is it not? That is how the scheme will work actually. Okay, this scheme needs 3 points. So what does it mean is, this scheme reinforces the fact that the water particle kinematics and structural displacements depend on adjacent nodes. That is the fact what is reinforcing. Okay. So let me expand equation 27 further. Any doubt here as on now? Please go back few minutes, see the whole scheme, how we started the problem from iterative equation of motion, and see few minutes. You must understand the flow, otherwise at the end of this lecture you will be thoroughly understanding it. Okay. Please go through it, few minutes, where we started and now where are we and what actually we are looking for. If you have any doubt you can ask me. In fact, I will give you a tutorial sheet on this. I will give you a tower, I will divide this into 10 parts, and I wanted to solve this problem for a given wave loading for a specific water depth and wave height and wave period. You write a program and try to solve this and show me the results. Okay, let us expand this Fi of t slightly in a different manner. Okay, because this takes care of the different nodes, we already saw that. I want to implement this itself into this body, so I will rewrite it again. So expanding equation 27 further. If we expand this, because I want to take this iterative scheme of the different node dependency into the body of the iteration itself, or into the body of the f of t. So now I can write f of t will now depend on, you remember this is actually a summation, I am expanding it and getting f of t now, is that clear? Depends on j is 1 to n half kj, that I summation I am removing, that is the node number, which is Vi of Vi plus Vi plus 1 of Vi plus 1, is that okay? That is what we also wrote earlier. If you look at two equations, again the numbers 11 and 12, I am writing it here back again, and kj stops here, that is my drag force, plus j is equal to 1 to n again half k bar j u double dot n plus 1, sorry, ni plus u double dot n I plus 1, this is I. I call this equation number 28, where kj and k bar j are given by the following. What I have done in equation 28 is I have just imposed the summation of nodes into this and expanded it on the basis of equation 11 and 12, which we wrote earlier. Now let us see what this kj and k bar j looks like. Shall I remove this? Where kj, we all know that still half rho CD dj Lj h of j. Now why I am multiplying with L? Because I am looking for the capital F of t here, is equal to, I am looking for the capital F of t here, I am multiplying the length of the member. Why I am looking for h of j multiplier here? Because I am looking for the moment of these forces about the base of the hinge. I am not looking at the forces at all, I am looking at the moments of these forces, is it not? Because my degree of freedom is rotation, not displacement. Is that clear? So that is why the multiply hj is there. And k bar j, obviously I think you can write this with an inertia component, which will be pi d square by 4 Cm, of course rho w. Nevertheless, we can write Vi in this equation is Ui minus theta dot, okay, that is a relative velocity, okay, theta h of I. Can you tell me what is h of j? Correct definition, anyone? What is h of j? This is not C, this is L. I rewrite it again here. This is L, length of the member, and this is subscript. Why I am multiplying with length? Because I am getting capital F of t. Small f of t was per unit length of the member. So I am multiplying this with L. Okay, fine. What is h of j? H of j is the distance of CG of the member jth member from where? Base of the tower. Okay. Now let us look at the derivative of one example. We picked up one derivative from the Jacobian, which is dou fms c by dou theta m c. Let us see how this looks like now, because I have expanded f of t. This will now become 2 by a record length of 0 to record length of dou of the derivative of f of t k nu t. This is not r of t, this is nu t of theta minus I beta t theta double dot by dou theta m c of dt. Which is expanded further because it is already written. Now the cos component and f of t has got again a cos component or a sin component, okay, depending upon what component you are looking in the Fourier. So, if you expand this further, let me do it here. So, I have to take a partial derivative of the cosine component of this mth frequency, and again there is a multiplier already available in m sigma t, and this has got 3 components 1, 2 and 3, okay. Let me do it here. That is going to be equal to 2 by record length of 0 to record length of, so I am taking a derivative, there is a cos m sigma, so m sigma summation of kj, I am just putting f of t, I mean the equation which I wrote earlier 28 back into f of t here, summation of kj hi vi plus hi plus 1 vi plus 1 of sin m sigma, that is the derivative, cos m sigma t dt. Is it okay? Minus there is a negative sign here, okay, minus k mu t 2 by RL 0 to RL k nu t theta, sorry theta is now substituted, which is going to be cos square m sigma t dt plus there is a negative sign here, the double derivative here, double derivative and displacement are related by a negative sign, they are out of phase by 180 degrees, is it not? So, this minus will become plus here, okay. 2 by record length of 0 to record length of m sigma the whole square, because this having m sigma multiplier, this is double derivative of that, okay, m sigma the whole square I naught beta of t cos square m sigma t dt. I think you agree for theta and theta double dot you will have the same term repeated except that there is a multiplier here, is that agreed, and there is a sign change, okay. That is what I have done here. I call this equation number 29, is this number okay? This is my dou fmc by dou theta mc, one value of a Jacobian, okay, only one value. I want to rearrange this term, I think I will stop here because there is only 2 minutes left over, stop here.